The X-32 didn't just lose an air show, it lost a $1 trillion logistics problem. The reason sits between thermodynamics and standardization, direct hot lift versus a shaft-driven cold fan. We'll walk the exact failure modes program managers worried about: weight creep, heat on the deck, integration headaches, and how the lift fan gave the X-35 just enough margin to scale across variants. Then we'll connect that to today's reality: software bottlenecks and latency when 4 aircraft fuse targets. If you want the family of jets, you need the family to talk. Here's why that started in the engine bay. Before we move on, please take a moment to subscribe to the channel and like the video. The fork came from one requirement written 3 ways: a single airframe family, shared production and sustainment, and a STOW VL jet that could land beside a destroyer without scorching it. So the design center moved toward hover first, because if the B variant failed, commonality failed, and the rest lost their anchor. Boeing proposed direct hot lift, vector the main nozzle down and feed roll posts with bleed air. Lockheed split the problem. Keep core thrust aft and send shaft power forward to a lift fan, with a 3-bearing swivel at the rear and roll nozzles at the wings. The stakes were not abstract. Hover brings recirculation. Hot exhaust wraps around the inlet and steals oxygen from the compressor, so thrust falls just when you need margin. And heat is quadratic in effect on decks. A small increase in temperature combined with longer hover time raises thermal loading sharply. So coatings that shrug at brief passes start to fail when asked to hold a sustained hotspot. The X-32 sent almost all of its core exhaust straight down in hover. The main nozzle formed the lift column, while small roll posts near the wingtips handled lateral balance. That meant the stagnation temperature near the deck sat close to core exhaust levels, and in crosswinds, the hot plume drifted under the intake lip and back into the engine. Short hover pulses were manageable, but prolonged holds near a ship or rough landing pad pushed ingestion and heat into the same corner. The X-35B decoupled temperature from lift by moving mass flow instead of heat. The F-135 core drove a clutchable shaft into a vertically mounted counter-rotating fan ahead of the center of gravity. That fan produced a broad column of cool, high-mass air. The rear nozzle vectored the remaining core flow, and roll nozzles trimmed attitude. The result was a balanced 4-poster feel without relying on hot gas for most of the lift. The physics favor cold thrust when the surface below is vulnerable. Fan discharge temperatures sit far below turbine exhaust, and the mass flow is substantially larger, so the jet velocity and temperature at the deck drop, even though total lift rises. Naval deck coatings tolerate higher mass flow far better than high stagnation temperature, and the ingestion margin improves because the air around the inlet stays cooler and denser. You get the same lift with less thermal penalty. Each path carried risk. The X-35B added mechanical elements: clutch timing, gearbox torque limits, and big doors that had to open, lock, and close on schedule. Failure there is binary. But the X-32 accepted thin thermal and ingestion margins that narrowed further with gusts, cross-deck winds, or prolonged hover, while its vectoring nozzle demanded precise control authority just as thrust degraded. Hover is binary as well. You either meet the vertical requirement with margin or you don't. As weights grow late in a program, hot lift systems tend to reach for higher turbine inlet temperatures or bigger nozzles, and both make heat and fuel penalties worse. The lift fan let designers buy extra lift by moving more cool air rather than heating the same air further, so the thrust rose without pushing deck temperatures or compressor face temperatures into the red. So the first payoff arrived early. The shaft turned into cooler, denser lift, which increased thrust per unit temperature and took the edge off deck heating. Handling in the hover steadied, the ingestion margin opened, and the ship integration problem shrank from a structural worry to a procedure. It was therefore possible to think about sortie rates and maintenance scheduling rather than firefighting deck tiles. Once the hover margins held with headroom, the family concept became practical. Sensors, cooling loops, and software could converge across variants because the B no longer forced thermal compromises into the baseline A and C. And that is where commonality stops being a slogan and starts paying in sustainment. The family idea sounds tidy, 3 variants from one architecture, but the constraint sat with the STOVL jet. The A was conventional takeoff and landing, the C was carrier with bigger wings and hooks, and the B had to rise and set down vertically with fuel and weapons left to bring back. Parts commonality, shared maintenance, and a unified software baseline only worked if the B could anchor the design without forcing everyone else into thermal and weight penalties they did not need. A direct lift, STOVL aircraft meets a late weight increase the hard way. If the airframe gains mass from structure, survivability, or new avionics, vertical thrust must rise to match. With hot lift, options are limited. Raise turbine inlet temperature, enlarge the nozzle throat, or accept shorter hover and reduced bringback. Higher turbine temperature accelerates thermal stress and fuel burn. A bigger nozzle lowers exhaust velocity at some regimes, but still sends a high stagnation temperature onto decks and pads, which tightens operating windows and pushes maintenance into the sortie schedule. By contrast, the lift fan splits power. Shaft horsepower forward becomes cool, high-mass flow, and the rear core still contributes. That adjustable split tolerates incremental weight growth because the system can deliver more lift by moving more air instead of heating the same air further. So the aircraft preserves thrust without pushing deck temperatures or compressor face heat into a corner. It was therefore possible to keep hover time, safety margin, and bring back weight inside realistic envelopes even as hardware accreted. Hover margins show the practical effect. If you add test instrumentation, new cooling loops, and additional defensive gear, you need a buffer above 1-to-1 thrust to weight in the vertical. With a lift fan, that buffer comes from colder flow, so the deck sees less heat for the same lift, and the pilot holds a stable cushion long enough to taxi, spot, and shut down. Bring back stays credible because you don't pay the heat penalty to lift every extra kilogram. You trade shaft power for airflow and keep the plume gentle enough that ship coatings and asphalt survive repeated cycles. Carrier integration reinforced the difference. Downwash footprints from a cold column are broader and slower, so exhaust impingement on deck hardware, elevator edges, and tie-down points remains within material limits more often. Hot plumes from direct lift concentrate energy into smaller areas and produce steep thermal gradients, which complicate where you can park tractors, weapon skids, and personnel. In any case, a colder plume simplifies choreography on crowded decks and lets the ship turn sorties without spacing each hover like a hazardous operation. Those margins unlocked common systems. With safer hover, the program could pursue shared sensors, common weapons bays, and aligned cooling for avionics across all variants. The thermal and electrical budgets stayed coherent because the STOVL case did not collapse them. That alignment mattered later when tactics moved to software-defined fusion. 4 aircraft combining tracks demand stable timing, consistent power quality, and sufficient cooling to hold processors at speed without throttling. Concurrency introduced its own risk. Software latencies stack when networks share targets and move high-rate data, and you only get away with that if the airframes carry similar thermal and electrical headroom. A direct lift baseline that runs hot and fuel-thirsty in hover would have forced unique cooling solutions and bespoke maintenance profiles, which breaks standardization. The lift fan's mechanical margin kept the budgets common enough that the software problem sat on top, not underneath. One way or another, Boeing's hot lift path struggled to scale without unacceptable compromises to heat, fuel, and deck operations. Lockheed's layout preserved weight, thermal, and integration margins so the A and C could remain aligned with the B, and we can now move on to the reason the family claim held together while software timelines became the pacing constraint. The lift fan wasn't showmanship, it was headroom. Thermal and weight margin turned a STOVL prototype into a workable architecture that could absorb growth and stay inside ship and pad limits while keeping the A and C aligned with the B. Cold thrust let commonality survive. Software then became the pacing issue. One source put it plainly. I would sum it up in one word: software. If you want to follow on, we can unpack the latency and fusion problem that came after the engine bay decision. How 4 jets share targets without moving them on the map. The trillion-dollar outcome began with a cold column and a small gearbox.